Welcome to the Flight Readiness Review for the Autonomous Aerial Vehicle Design Team at Virginia Tech. Over the next 10 minutes, we will provide you with a brief overview of our UAS and flight testing to ensure that the aircraft is mature enough to compete in the 2022 AUVSI SUAS competition. Introducing Jaeger, a custom multi-copter that was specifically designed and developed for the 2022 AUVSI SUAS competition. The base airframe consists of 4 arms, 2 center plates, and 2 landing legs. In order to maximize strength and minimize weight, the airframe is composed primarily of carbon fiber with aluminum reinforcements at high stress concentration locations. The propulsion system is composed of KDE 360 kV motors, KDE 55 amp ESCs, and ZOR 1865 carbon fiber propellers. When paired with a 6S 22 amp hour LiPo battery, this propulsion system is capable of providing upwards of 4.5 kilograms of thrust per motor. This singular battery is also used as the power source for the autopilot system and all payloads. At competition weight, Jaeger has a minimum thrust to weight ratio of 2.09 to 1 and is capable of traveling at max horizontal speeds of 55 knots. Jaeger's autopilot system consists of a Cube Orange and a Here 3 GPS. With power and voltage data from the electrical system, Jaeger is able to recognize and react to any power failures in a timely manner. The autopilot system communicates to the ground via 2 communication bandwidths, 900 MHz and 2.4 GHz. The 900 MHz bandwidth is used to connect Jaeger to the ground control station, while the 2.4 is used to relay communication between the radio controller and Jaeger. The Cube Orange's internal redundancy and dual communication pipelines established allow for a fully redundant autopilot system. In order to complete the airdrop task, Jaeger carries on board a fully autonomous UGV and delivery mechanism. With direct communication to the Cube Orange, the delivery mechanism utilizes a custom-designed winch system to safely lower the UGV. In addition, the winch's release mechanism utilizes redundant servos to ensure that the UGV does not disconnect from Jaeger during flight. The custom UGV is a front 3-wheel drive configuration outfitted with a Cube Orange and a Here 3 GPS module for fully autonomous navigation and ground impact detection. Located just next to the airdrop system is Jaeger's imaging system. This system is composed of 3 components: a Sony R10C mapping camera, 2-axis gimbal, and entire R3 geotagging module. All components work in tangent to provide Jaeger with the ability to attempt the ODCL and mapping tasks. Through multiple hours of testing, all systems upon Jaeger and the UGV have been verified in their reliability and ability to complete tasks. When traveling at a cruise speed of 40 knots, Jaeger is capable of traveling 15 plus kilometers. In the following section, we will describe an overview of what is expected of Jaeger during the mission demonstration. All aspects of autonomous flight, takeoff, landing, and waypoint navigation will be attempted with high confidence. Stationary obstacle avoidance will be attempted with high confidence. Moving obstacle avoidance of other aircraft in the area will be manually conducted with high confidence. Both stages of airdrop will be attempted with high confidence. Object detection, classification, localization will be conducted with medium confidence. Mapping will not be attempted. Information regarding this exclusion will be covered in its upcoming section. In order to mitigate the probability of issues arriving mid-flight, AAV utilized multiple developmental testing procedures. During the season, AAV followed a 3-step testing procedure known as SII, or Simulate Individualized Implement. During the design phase, several static and dynamic simulations were conducted to generate a high structural integrity airframe. Once manufactured, AAV conducted dynamic load testing via Jaeger's onboard propulsion system. Before mounting any critical payload to Jaeger, a controlled test was performed with a 1.5 kilogram mock payload. The mock payload was loaded during tuning flights and verified Jaeger's ability to safely operate prior to integrating the real payload. Before being uploaded to the UAS, custom algorithms were simulated through an SITL environment. This allowed for testing against any edge cases without putting the UAV in danger of a crash. After passing all initial stages, the algorithm was then cleared to be integrated into the UAS. During flight testing of newly implemented algorithms, AAV ensured flight safety by implementing several fail-safes and backup protocols. In order to assure reliable autonomous operations, 10 test flights have been conducted with the system in competition configuration. Following the maiden, a flight specifically designed to tune Jaeger's PIDs by using rapid in-flight movements of different aggression levels was conducted. After being used, Jaeger spent an additional 180 minutes in the air, 95% of which were fully autonomous. Jaeger has flown a total of 6 flights with autonomous waypoint navigation activated. This accounts to 120 minutes of flight where Jaeger has attempted 79 waypoints, hit 79 waypoints, and has had an average waypoint miss error of 1.43 feet. As per obstacle avoidance, Jaeger has flown 5 autonomous flights while attempting to complete the obstacle avoidance task. Due to the automated nature of AAV's solution, Jaeger was able to avoid all of the 12 obstacles it was tested against. After extensive training with the ground control station, AAV was also able to increasingly become aware of such extreme cases, such as obstacles in close proximity to other competition elements. In order to ensure high-quality images during flight, AAV has chosen to use a mirrorless camera that is able to capture images at 20 megapixels. Because the ODCL and mapping algorithms require the camera to be pointed directly at the ground, a 2-axis gimbal was integrated into the imaging system. By monitoring the imaging quality at several cruise speeds, AAV was able to fine-tune the damping mechanism used to attach the imaging system to Jaeger. At the optimal flying altitude of 350 feet, the system is able to produce an image quality of 2.85 centimeters per pixel. This ground sampling distance proved adequate for manual detection and classification of objects. Through the use of a manual ODCL GUI, AAV is able to achieve high accuracy in its detection and classification of objects. Extensive training with AAV's ODCL GUI has also led to rapid detection and classification of objects at an average scanning rate of 10 images per minute. Unfortunately, Jaeger is not outfitted with in-flight image transmission capabilities, and thus all processing occurs in post. Jaeger will also not be attempting the detection of both the off-axis and emergent objects due to a lack of testing. These limitations have a slight effect on the maximal score achieved for ODCL, but allows for a more simplistic process. In an attempt to increase localization accuracy and reduce the need for manual calculations at the flight line, an autonomous localization algorithm was created by the team. In order to maintain high precision, the entire R3 module automatically inputs aircraft location and heading data into each image's metadata upon capture. When tested against the 10 manually detected objects, the algorithm was able to localize the targets with an average deviation of 20 feet. As previously mentioned, the mapping task will not be attempted at the 2022 AUVSI SUAS competition. This is due to a lack of testing that stems from its relatively low scoring potential of 10%. Thus, a larger focus was placed onto the task carrying a higher scoring weight, such as airdrop and ODCL. AAV hopes to attempt this task at the 2023 AUVSI SUAS competition were it to continue. The delivery system and unmanned ground vehicle have been tested in numerous flights on board Jaeger. The delivery system was first tested with mock payloads that represented the UGV. This allowed for rapid improvement of the delivery system without putting the UGV at risk. After extensive training, AAV was able to tune the tether length and drop timing for reliable deliveries. The result of the 6 attempted deliveries showed that the UGV lands with an average accuracy of 6.75 feet from the target. Independent of the delivery accuracy, the UGV survived and was able to navigate within 10 feet of the target location in all tests. 2 full mission tests were conducted with Jaeger in competition configuration. A distance of 6 miles was used to replicate the maximum range required for waypoint navigation. Randomized obstacles were scattered throughout the flight area to ensure no prior planning was conducted before receiving the mission. Air delivery was conducted over a runway that matched the terrain depicted in the UGV boundary area given by the competition. 10 objects were spread out over a 100-acre search area for replication of the ODCL task. As mentioned, the mapping task will not be conducted at competition and was thus not included in these full mission tests. Throughout these tests, AAV was able to ensure that all failsafes and algorithms were operating as predicted. The flight personnel were also trained for efficient usage of the 20-minute flight setup time allotted at competition. During the 2 mission tests, AAV achieved a total mission score of 71.74% and 65.34%. Although all objects within the search grid were found, an object search rate of 10 out of 12 was given to account for the emergence of off-axis objects that will not be searched for at competition. The main scoring difference between the 2 mission tests is due to the first airdrop achieving a delivery accuracy of 3 feet, with the secondary airdrop achieving a delivery accuracy of 12 feet. The difference is due to environmental conditions such as wind that are ignored when conducting the UGV delivery sequence. During the mission demonstration, AAV plans to score equal to their average mission test score at 68.54%.